Alright, we're finally ready to put some numbers to these bad boys. In the last couple of videos I've explained what a solid revolution is and how we can slice it up into various shapes to add them up to the weird shape. So let's get started. Now basically this is all based on the same concept as Riemann sums. So if you recall, Riemann sums are where when you wanted to find the area of a region, you would break it up into a bunch of vertical or horizontal rectangles, figuring that, hey, if the rectangles somewhat were the same shape as a region, then if you add up all those rectangles, the area of all those rectangles added together would give you the region. Now we're just going to do the same thing with volumes, and we'll need a formula to do that, obviously, the disk formula. And in the next couple of videos, we'll cover the shell method and the washer method, but it's just several different formulas that we can apply to these situations. And they are hard to apply. I mean, this is not easy stuff, but ultimately that's what's going on, is we just need to learn how to plug and chug and do it the right way every time. Alright, so as I've explained in the previous video, the disk method is basically if your shape, like your weird shape, like on this previous slide we had a ball, so we're like, hey, let's take a sphere, and maybe I don't remember the offhand the formula for the volume of a sphere, so what I could do is cut it up into a bunch of disks, like literally flat round circles with a little bit of thickness to them, and then the volume of each one of these disks, I can add up all those volumes of each individual disk, each of which is a slightly different size. So the question is, what is the volume of each disk? Because in Riemann sums, when I had, if I had a region and I sort of turned it into a bunch of rectangles, and I added up all those rectangles, and the rectangles sort of followed the curves there, the area of a rectangle is really easy to find. It was just base times height. So it was the width of this little rectangle times the height. And in this particular case, the height turned out to be, like if this was f of x up top, and this was g of x down here, then the height would just be f of x minus g of x, and then the width was either 0.1 or 1 or something, or later on we did integrals and the width was dx. But the point is the area of the rectangle is what mattered, right? So if you're going to add up rectangles, you need area of rectangle formulas. If you're going to add up disks, you need the volume of each disk. So the way you find the volume of a disk, turns out you just find the area of the disk, and then you multiply by the thickness. So if you know the area of this circle is that, and then the thickness is thickness, you can just multiply the area of the disk times the thickness of the disk to get the volume. So that's going to be pi times the radius of that disk squared. And then really key thing is when we use integrals, the thickness is going to be dx. Because if you look at this little dimension, it's just like the width of these little rectangles was dx, because that little width is in the horizontal direction, which is the x direction, which means that so that's why it's dx for width this way. And then if we ever drew rectangles sideways like that, the thickness was dy. Same thing with disks. If you have disks that are vertical, the thickness is dx, so dx is going to be our thickness. And then if you have a different kind of problem where the disks are horizontal, no big deal, but the thickness becomes dy instead. So this is the volume of a single disk. It's pi r squared, where r is just the radius of that disk. And of course r is going to end up being like the functions we're using. But then dx is the thickness. So a really key concept is always think of the dx or dy as the thickness. And actually I'll try to remember to do it for every problem, but we're always also going to draw on these little rectangles. So even though we're doing volume problems, I'm going to draw on a representative rectangle each time so that to really show me whether I'm doing dx or dy for that problem. That's a really key step. Alright, so now that we figured out the volume of each individual disk is just pi r squared dx, how do we add up infinity disks? How we get from one disk to all the disks that are going to add up to this area? Well, we integrate. Same thing with area between curves. As soon as you do an integral, so if we just wanted to find the area of this region, we would have just integrated from a to b times f of x dx, and that would have given us the area under the curve, right? Because what an integral does is it takes a region and sort of splits it up into infinity little rectangles, each of which is dx, and dx is really tiny. So if you want a super accurate Riemann sum, you have to do a ton of rectangles. Same thing here, we're going to do a ton of disks. Actually, the limit is the number of disks that approaches infinity. So that's what an integral is. It's just going to say, you know what? By putting this integral from a to b and this dx right here, I'm going to add up infinity disks, each of which is pi r squared in area. But what the heck is r? What do we put in for r? Well, it turns out that if you look at this region, so here we've got a sort of upside down parabola, and we're going to spin it around this spin axis down here. So that's what this little curlicue right here means. It's sort of like, that means we're going to revolve this parabola thing around that spin axis. So we're going to get kind of a flying saucer shape. So something like that, like a rollerblade wheel or something. So when we spin that up, what is the radius of each individual disk? Well, it's just always going to be the function. So if this is the x-axis, then the radius of this first disk, if we sort of draw it in, it's going to be a disk about that big. Then this next one is going to be a round disk that big. It's going to go all the way down there. But again, that radius is just the y-coordinate of this point right here. Because remember, this curve is f of x, so every point along it has a y-coordinate of f of x. Once I get to the biggest disk, the sort of outside radius, the fattest part of the rollerblade wheel, that's right here, and the radius at that point is all the way from here to here. So that radius, it looks like it's 3 or 4 in this drawing, which means that when I spin this thing around the axis, it's going to form a disk that goes way here off the screen. You know, crazy huge disk. And then once we get down to here, we'll start making, start making smaller disks again. And this guy will be smaller and smaller. So we'll end up with sort of a reflection of the parabola down below here, and there's my rollerblade wheel. So what's happening is, if you just take this r in r squared and replace it with the function is your r. Because as you go from one rectangle to the next, to the next, to the next, they're all different sizes. But the height of each of those rectangles is determined by the functions. That's why you stick in the function for r. Now a little bit, some slightly wackier stuff is going to happen when our spin axis is not the x-axis. So like this particular one I just drew, I'm spinning it around the x-axis. Turns out if we spin it around a horizontal line that's above or below the axis, that's a little tougher. But all we're going to do is just stick in an extra number here. We're going to stick in a plus c, like a plus 1, plus 2, minus 1, minus 2, that kind of thing. Not the end of the world, but that's the formula. So this is the formula we're going to use from now on for the disk method. And I've just tried to explain a little bit of where it comes from, and I know it's going to sound a little bit like Greek, but if you go and watch this video, learn how to do the problems, then come back and watch this first part again, it might make a little more sense. Because sort of the most confusing part of these problems is trying to understand them, and then if you just plug and chug, you can actually do pretty well. Alright, so here's an example. Let's find the volume of a cone. So why is this thing a cone? Well, let's see, we got x equals 0, so that's just a y-axis. So what they're always going to do is give you a region, just like when you're finding the area. So they'll give you x equals 0 is this thing right here, y equals 0 is the x-axis, and then y equals 4 minus x I already graphed, so I wouldn't have to draw a really bad straight line. So this is the region. Alright, so they want us to take this region and revolve it around the x-axis. So whenever they tell you what your axis is, you need to draw in an arrow, the little curlicue, just to remind you, hey, that's my spin axis. You really want to put that on the drawing. So step 1 of these problems is always draw the region, drop in the spin axis. Alright, so what is step 2? Step 2 is we got to figure out what the formula is. But here it is. We're all good. So we're spinning around the x-axis, and something really important about disk problems is that our little representative rectangles, they're going to be perpendicular to the spin axis. So on all those drawings I just showed you, here's one of our little representative rectangles. If I spin this rectangle around the horizontal axis, if I want to make a disk, it's got to be like that. If I spun a sideways rectangle around that horizontal axis, I'd end up with some kind of crazy tube shape. That's going to be the shell method. We'll do that later. Right now, for both disk and washer method, your representative rectangle thing is perpendicular to the spin axis. And the reason I drew in this representative rectangle is so it'd be really obvious that the width here is dx. So that's why I'm using the dx formula. And another way to do it is just memorize that with the disk and washer methods, if you have a horizontal spin axis, it's a dx problem. If you have a vertical spin axis, it's a dy problem. So it's however you do it, however you prefer to do things, memorize them or figure them out from the drawing. Either way, if you got a horizontal spin axis with the disk method, it's a dx problem, which means we need f of x. Alright, so let's just start plugging and chugging. So first I got my pi. What are my limits of integration? My limits of integration are just the range of x coordinates. Since I'm doing dx, these limits refer to the x direction. So what is the sort of range of x values that this problem covers? We're going from 0 to 4. You can get that 4 from the graph in this case, or we could have just taken this thing up here and set it equal to 0 to find the x-intercept. So 0 to 4, and then I got f of x, which is just 4 minus x. So the f of x is just whatever curve the other end of the rectangle is following. Because on the disk method, since there's no hole in the middle of the object, one end of the rectangle is always on the spin axis. And then the other end of the rectangle is going to follow a curve or something, which in this case is just this line. So that's just going to be 4 minus x, and we got to square it. It's really easy to forget the squared. That's like the #1 thing that I do and that I've seen students do to mess up these problems. I really recommend always writing the formula out. Even if you've done a lot of these and you pretty much have it memorized and you think you totally know it by heart, still a really good idea to write down the formula just with all variables still, just like the raw formula, so that you can plug and chug, just go piece by piece, and that way you'll never forget any squares or cubes or whatever that case happens to be, whether it's shell, disk, or washer method. Alright, so at this point we got this thing. Now I could start integrating, but it seems like the easiest thing to do would be to FOIL this out. I personally prefer to FOIL out polynomials. So we got 16 minus 8x squared plus x squared all times dx. Alright, so that's going to be pi. Now I can integrate. So we got 16x minus 8/3 x cubed plus, oops, sorry, that's x. Alright, so that's minus x integrates to x squared over 2, so that's 4x squared plus 1/3 x cubed. And that is from 0 to 4. Alright, pi times, so 4 times 16 is 64. Minus 4 times 16 is also 64. So those just cancel right out. And we got plus 1/3 times 64. Alright, that's what I got before. Now, sometimes with these revolution problems, there's actually a way to double check your answer. And that is that frequently you're doing a shape that you actually learned how to find the volume of back in geometry. So if you recall, the way to find the volume of a cone, it's 1/3 pi r squared h. So that's 1/3 pi, and then r is just the outside radius of the base, which in this case would be 4. Actually, since we're spinning this way, the base is up here. But either way, since this is a 45-degree angle, they're both 4. 4 squared times h, which is also 4. And sure enough, 4 squared is 16 times 4 is 64 over 3. So 64 pi over 3. Really cool. So we just got the same volume with the volume formula and the volume integral. Nice work. Alright, find the volume of 1 minus x squared. Alright, so our region is 1 minus x squared, which is upside down parabola, and y equals 0. So here's our region. Revolved around the x-axis. So once again, we're going around the x. In a second, we'll see what it's like to go around the y-axis. Really just switch all the letters around, but it's not very different. Alright, so we're just going to plug and chug. Looks like we have another one that's spun around the axis, which means we don't have to add any numbers in. We're just going to integrate. So our limits of integration, and again, there's a dx problem, because if I draw in my little rectangle here, it's a vertical rectangle perpendicular to the spin axis. So that means my width here is dx, the width of my little rectangle. So since the dx problem, we need the range of x values. You know, our a and our b are just the sort of range of x values. Looks like we got a -1 to 1. And we're finding those the same way that you found the limits of integration when you were finding the area between curves. So as far as looking at the region and analyzing it, it's just like when you found the area between curves. So -1 to 1, and then we get a pi. Throw a pi out front. And then we got f of x, which is 1 minus x squared. And then that gets squared, and we got a dx. Alright, so that's pi times the integral from -1 to 1. And I'm going to FOIL this out. This one actually you could not integrate unless it FOILed out, because your du's would not match for the power rule. Minus 2x squared plus x to the fourth dx. Alright, so now we'll integrate. So we get x minus 2/3 x cubed plus 1/5 x to the fifth, all from -1 to 1. Alright, good stuff. So you can see how this is going to get a little bit messy here. So I'm just going to plug in the top limit of integration first in its own set of parentheses. So let's see, 1 minus 2/3 times 1, so 1 minus 1/3 is 1/3, plus 1/5, minus, and then we plug in -1, we get -1 minus -2/3, so that's -1/3. Oops, don't need a comma. And then plus 1/5, but it's the -1 to the fifth is -1, so minus 1/5. Alright, now you'll see something interesting happen here, and this is going to happen a lot. Because we have sort of a symmetrical shape here, it goes from -1 to 1, you can imagine the volume from the left half of this region is going to be the same as the volume from the right half of the region, because it's like two halves of the same thing. So that's why this and this are identical expressions. Because this negative is going to cancel these negatives, and we just end up with 1/3 plus 1/5 plus 1/3 plus 1/5. So that is going to be pi times 2/3 plus 2/5. Looks like we got to do 15ths here. So 2/3 can be 10/15 plus 6/15 equals 16 pi over 15. Wacky. Alright, so that's pretty much what happens with dx problems. Let's check out dy. Alright, so now we've got a dy problem. What does that mean? Why would I have to use dy? Well, it's actually the same reason. I should have made this y. It's actually the same reason that when you're finding areas of a region, you might have used dy instead of dx. And that is, you have to. Now maybe they ask you to use dy. In this particular case, we actually have to if we want to use the disk method, because check it out. Now we're revolving around the y-axis. So it's the same region we used in the previous problem. This puppy right here, so it's going ding, all this stuff in here. But now the spin axis is the y-axis. That's what we're going to revolve this thing around. So that means that this thing is a cone this time. Instead of being a sideways cone like that, now it's a vertical cone like that. So that means its circular cross sections are sideways. It's a bunch of disks stacked up vertically, which means our disks are flat or horizontal disks. Which means I got to use horizontal rectangles, and therefore their thickness is in the dy direction. Okay, so that's why we have to use dy all of a sudden, but the formula is exactly the same. We just switch all the x's to y's, and now we're right back to usual. With one subtlety I'll show you in a second. We have to have functions of y, not x. So that means y equals 4 minus x isn't quite right. We need x as a function of y instead of y as a function of x. So the only subtlety here, let's see. So we're going to do dy. So let's plug and chug through the formula. I have a pi out front. My lower limit of integration. Now this time we're doing the range of values of y, not x. Because since we have a dy, our a and b is what ranges of y this region covers. Looks like it goes from 0 up to 4. Alright, now here's the tricky part. F of y, I could just write down 4 minus x. But the problem with that is I've got a dy. So how do I integrate x's with a dy? I can't do it. That does not work. So what we're going to do instead is we've got to rearrange this equation to have it in terms of y. So we're going to solve for x, which means we'll just add x to both sides. So x plus y equals 4. And then we'll try and get x by itself by subtracting y. So we'll get x equals 4 minus y. Alright, so that means our function in terms of y is 4 minus y. So this is one of those ones where the x and the y versions look exactly the same. Y equals 4 minus x versus x equals 4 minus y. That's not always going to happen. If there was an exponent in there, you'd probably have roots instead of exponents, that kind of thing. And we'll see a bunch of those in the washer and shell methods where the switch from x to y is more dramatic. But for this one, it's really simple since it's just a line. and we got a dy. So now you can see I got y's everywhere, no x's, which means I can just integrate totally normally. So, oops, oh look at that, forgot to plug and chug the squared. See, so easy to mess these up. All right. Although that said, I do make less mistakes when I'm not talking at the same time. All right, so now we got to square this out. We could, again, integrate this using the power rule, but I say, hey, why mess with that? Suppose plug it, we'll just FOIL out the 4 minus y quantity squared. So that'll give us 16 minus 8y plus y squared dy. All right, so that's going to equal pi. And now I'm ready to integrate. So I got 16y minus 8y squared over 2 is 4y squared plus 1/3 y cubed, and that is from 0 to 4. So it ends up actually looking just like the integral we had in the x direction, and that's because this particular region, you know, it's as tall as it is wide. It's a isosceles triangle. All right, plug in the upper limit of integration. 4 times 16 is 64. Minus 4 times 16, oops. Yeah, I remember that happening last time. Plus 1/3 y cubed, 64. All right, so that's what happened when we plugged in 4. Now we plug in the bottom limit of integration, and we get 0. It's one of the great things about integrating from 0 to something. So we just get 64 pi over 3. Same thing we got last time. All right, so that's dy. All right, revolved around the y-axis. So we got yet another region revolved around the y-axis. So before I even draw the region, I'm going to make sure I emphasize that my spin axis is right there. What I'm trying to draw is a little arrow going around a circle. I don't always succeed unless I go really carefully, but that's the idea. All right, so around the y-axis, and what's our region? So we got 4 minus x squared, so that's this thing. Then x equals 0 is the vertical line, and y equals 1. So actually it's this whole thing right here. And just for giggles, I cut it off. I didn't make it go to the x-axis. I made it just go to this horizontal line, y equals 1, just to show. But 4 minus x squared not going to work for us because that has an x in it. All right, so this is a dy problem. Well, it looks like I'm ready to plug and chug though. Let's give it a shot. So I got pi out front. Then I'm doing a dy problem because again I have a vertical spin axis, which means if I draw on my little representative rectangle, that's going to, you know, form a disk, kind of right here. This disk has a thickness of dy, so that's why we got to use dy on this one. The y range goes from 1 to 4 this time. And what else we got? Oh yeah, so I need something, and this time I'm going to put in parentheses and then square it because I don't want to mess that up again. All right, so what is the function that's going to go in here? Well, it looks like the outside of all these disks is going to follow this 4 minus x squared. The problem is I can't just drop in 4 minus x squared because that has an x in it, and I need it in terms of y. So I've got to take this puppy and solve it for x. So first we'll just recopy it. Y equals 4 minus x squared. So solving for x, I'll get x squared equals 4 minus y. So if I add x squared to both sides and subtract y. So square root both sides, and we get that x equals square root of 4 minus y. Now you might be wondering, why did I not put in a plus or minus? And true, I could have done that. Could have put in a plus or minus. The plus refers to the right-hand half of the parabola, so this half is the positive one, and then this half is the negative one. But we only need the positive one because we're just looking at the right-hand half of this puppy. So that said, though, if you'd use the negative one, it wouldn't really matter. It's going to get squared away anyway. All right, so right here, in here, we're going to plug in square root of 4 minus y, because that's the same parabola, just in terms of y instead of x. Now I'm ready to go, and this sum's going to happen here that happens a lot in these problems. Whenever you have a big square root, it turns out to not be a problem, because when you square it, the square root goes away, because the disk formula and the Washer method also have a built-in squared here. So if you put in a square root, that's fine, it just gets squared away. So we got pi times the integral from 1 to 4. Square root of 4 minus y squared is just 4 minus y. Easy integral to do. Oops, don't need that anymore. So pi, ugly pi, times 4y minus 1/2 y squared from 1 to 4. Alright, so we've got to be careful here. Pi, so 4 times 4 is 16, minus 4 squared is 16, times 1/2, so minus 8. Now I got to plug in 1, so it's going to be 4 minus 1/2. Alright, so that equals pi times 16 minus 8 is 8, minus 4 minus 1/2 is 3.5. So 8 minus 3.5 is going to be 4.5 pi, which is 9/2 pi. Or 9 pi over 2, however you prefer it. In calculus, it's no problem to use improper fractions, so we don't have to worry about reducing things or anything. Alright, tough one. I wonder why. Revolve the region, around the line y equals 3. Yeah. Interesting. Alright, so we changed up the region a little bit. Even though we're using the 4 minus x squared again, I like to use the same function again and again. Just to show you guys how you can take the same function and mix it up into different types of problems, because it really brings out the subtleties of each individual region if we use the same curve a lot, but then we slice and dice it different ways. Like the last time, we spun it around the y-axis, and we only used half of it. But now we're going to spin it around the line y equals 3, which is a horizontal line. So here's our spin axis. So that's weird. It's horizontal, and it's not the x-axis. Everything we've done so far has either been the x-axis or the y-axis is our spin axis. We're just going to have to throw in a number to compensate for the fact that it's not. All right, so the region is between 4 minus x squared, so that's the parabola, and f of x equals 3, which is just the same horizontal line, y equals 3. Because f of x and y, same difference, right? So this is the region. And since it's disk method, pretty much you have to have the same spin axis as one of the boundaries. All right, so here's our region. Goes from the spin axis up this parabola. And what else we got? So this point and this point are going to be -1, x values of -1 and 1. And if you don't see that, you can just try solving. Set 4 minus x squared equal to 3 and solve for the intersection points, and you get plus or minus 1. All right, so is this a dx problem or a dy problem is the first question we always ask ourselves. And it is a dx problem, because there's our represented rectangle, because we're going to be making disks vertically. This is going to form like that, and we'll have a bunch of round cross sections throughout this thing. So the trick here is we've got to make up for the fact that the radius is not, that we're not spinning around an axis, but we're spinning around something with a number to it. This 3 is going to mess things up. But it's no big deal. We'll just have to stick in a 3 to the problem. We'll just have to be careful about where we stick it in. All right, so what do? I think we plug and chug. Why not, right? Because we know it's a dx problem. So we got the integral from x is going from -1 to 1. Put our pi out front. Now the tricky part here is going to be, what do we use for a radius? And of course it's still squared. Because the old radius, normally all our disks were centered. If you're revolving around the x-axis, for example, then your radius would just be all the way from the curve all the way to the x-axis. So that's just f of x. That distance is just a y-coordinate of any point along the curve. But on this one, it's a little bit different. On this one, like right here, if we spun this point around, it used to form a disk that went all the way down to here if we'd spun around the x-axis. But since we're spinning around this line right up here, there's actually a disk. That disk has 0 diameter. The biggest radius we're going to have of any disk is right in the fat part here. Is only going to be a radius of 1, and then it goes back down to 0 again. So what we got to do is subtract 3 from f of x. So it's going to be f of x minus 3. Pretty weird. But let's see what happens if we do that. So basically the new formula is going to be f of x minus the coordinate of the spin axis. So I'll just write that out, from A to B of pi times f of x minus c dx. So c is just the coordinate of the axis there, which in this case is 3. All right, so we got pi times the integral from -1 to 1 of some stuff squared. The stuff being, so f of x just 4 minus x squared, and then we got to subtract 3. All right, so this looks like a horrible foiling nightmare, except the 4 and the 3 actually combine. So we got pi times -1 to 1. 4 minus 3 is 1. All right, now for those of you keeping track at home, the region, if you look at this integral, it actually ended up being, it's almost like we just shifted the parabola down by 3, because 1 minus x squared is just this parabola. So from -1 to 1, same region, all we did is we just moved it down to the x-axis, basically, and then spun around the x-axis. That's what this integral represents. So at this point, we just plug and chug. Pi times, oh man, I forgot my squared. I am crazy. So easy to forget the squared, I'm telling you. So that's going to be 1 minus 2x squared plus x to the 4th dx. Alright, it's going to be pi times x minus 2/3 x cubed plus 1/5 x to the 5th from -1 to 1. Boy. So that's pi. Alright, so when I plug in 1, I get 1 minus 2/3 is 1/3 plus 1/5. And I subtract, I got to plug in -1. I think we went through this drill before. -1 minus a -2/3 is -1/3. And then -1 to the 5th power is -1 times -1/5 is -1/5. So that negative cancels these two negatives. And I get pi times, this was 2/3 plus 2/5 gave me 16/15. All right. Now this problem is a little bit tricky, but it's sort of nothing compared to what they'll do to you in washer method. So the truth is that they sort of introduced the disk method with some pretty easy problems just to sort of introduce the concept, but then all the harder stuff with weird spin axes and stuff are usually you're going to use washer method or shell method. So we're going to talk a lot more in those videos about how to deal with axes that are weird, because that's going to happen in like pretty much every one of those problems. All right, revolve the region around the line y equals 1. All right, so same story as what we talked about a second ago. So we got y equals x squared and f of x. So we're spinning around y equals 1. You'll notice that's also the bottom boundary, the top boundary of our little thing here. So this is x squared, and then we're revolving this region. So you'll notice what's going to happen this time is the same thing that happened before. But what's weird is we're going to flip things over. So this is going to be pi, and then it's a dx problem because if you draw on a representative rectangle perpendicular to the spin axis, its width is in the dx direction. So that's why we got a dx right here. Now we got to integrate what's x covering from -1 to 1, just like the last one. And all right, so what is the radius? Something we got to square dx. So what goes in there? It's actually, if you look at this little distance, you want to know the radius of any given little circle. I'm going to zoom in here to show you this. So here's our region. It's the bottom of a parabola. So the question is, the radius of any little disk, there's a radius, there's a radius, there's a radius, there's a radius. So the coordinate of any one of these points is just x comma f of x. And that's true of here, that's true here, that's true here. And of course, as x moves along this region, we'll get different f of x's, right? But the way you find the coordinate anywhere on a curve is just take x and plug it into f. So that's why f of x is the y coordinate for any one of these points. But what's the y-coordinate of every single point along the spin axis? They're all 1, right? They're all x comma 1. Something comma 1, something comma 1. The y-coordinate of every single point along the top here is 1. So if you want to know the length of any one of these little rectangles, all you do is you take the difference in y between the top and the bottom. So you'll take 1 minus f of x, 1 minus f of x. It's always 1 minus f of x. So that's why the radius, so since each one of these rectangles is 1 minus f of x, that's what our radius is going to be, is 1 minus f of x. And of course it gets squared and stuff, but now we just plug and chug at this point. So in the next video is about washer and shell. Those are harder problems usually, so I'm going to show you some plug and chug ways to get through those. But -1 to 1 of 1 minus x squared dx. And at this point it actually ends up being the exact same problem we worked last time. And of course, as we've seen, that turns into 16 pi over 15. All right, pretty cool, right? All right, last problem we'll do in the disk method, because like I said, you pretty much never use the disk method again. From here on out, you actually just use the washer method, and then if there happens to not be a hole in the middle of the thing, the inside radius will just be 0. But all right, here we go. Deriving the formula, the volume formula for a sphere. So you may recall that the volume of a sphere is just 4/3 pi r cubed. Let's see if we can get that using revolved stuff. Alright, so first of all I need a region. And you notice they did not give me any functions. But how would I make a sphere from common household items? I'd have to take a circle and spin it. So if I took half a circle and spin that puppy around this axis, I should get a sphere. So what is the equation of a circle? Well, it'd be x squared plus y squared equals r squared. Which means if you solve for either x or y, which one do I want to solve for? Well, if I might as well just use dx because I like dx. I could have done this problem in the dy direction and sort of rotated everything 90 degrees. But let's just do a dx deal. So that means we need this thing solved as a function of x. So it turns out that y is going to be the square root of r squared minus x squared. Just we rearrange this problem. All right, then what's my limits of integration? I'm going to go from -r to r. Now I'm not plugging in numbers for r, I'm just using r, because obviously in the final formula, I don't want it to be for some specific circle that happens to be diameter 5 or something. I want it to have r in it, so that I can plug in any sphere to it. So that's why I'm going to use r for everything. That's why I can leave r squared here, and I can leave my limits of integration as from -r to r. So let's do that. Let's integrate. So we plug and chug through the formula. AB r squared dx. As I've said, it's a really good idea to write down the formula in letter form before you plug anything in. So now I need the radius squared, and the radius is just going to be, each one of these vertical rectangles is just going to follow along that curve, right? Their bottoms are all along y equals 0, and their tops are all along the circle. So that's the length of each rectangle is just this function right here, f of x. Or to say that like a simpler way, if your spin axis is either x-axis or the y-axis, your r is just f of x or f of y. It's only when the spin axis is something else that you got to do f of x plus a number or a number minus f of x. All right, and then we got a dx. All right, so you'll notice that once again, very fortunately, the square root, which could have been pretty scary to integrate, gets canceled out by the squared. If you ever come across something you cannot integrate with a disk or washer method, it might be because you forgot the squared that would have canceled out the square root. All right, so all that cancels. We get -r to r of r squared minus x squared dx. That's an r. Looks like a v. All right, so pi. What's the integral of r squared dx? Well, r squared is just a constant. R is a constant, so it's not like I'm going to integrate r squared to being r cubed over 3. It's actually just r squared. But then it's a constant, but then of course integrating dx you get an x, so it's going to be r squared x minus 1/3 x cubed. From negative r to r. Alright, squared cancel, looking good so far. Let's see what happens. Alright, so when I plug in r, the top limit, I'm going to get r squared times r is r cubed minus 1/3 r cubed. Then I got to subtract, and now I'm going to plug in negative r, so I'll get r squared times negative r is negative r cubed, and then minus negative r cubed is negative r, quantity cubed is negative r cubed times negative 1/3 is positive 1/3 r cubed. Alright, so this negative sign has to get distributed in, so do that and do that. So we got pi times r cubed plus r cubed is 2r cubed. And then minus 1/3 and minus 1/3 is negative 2/3 r cubed. And sure enough, 2 minus 2/3 is 4/3. Pretty sweet. Alright, so the magic works. Now this is I picked this particular problem because it seems like it shows up in more than one book. And your teacher, if you have a really mean AP teacher, you might have to do something like this on a quiz or on the test. But really I just want to show you that, you know what, those magical formulas that you've been given all these years for cones, and we did a cone earlier and now we just did a sphere, those actually come from someplace. They come from calculus. So that's one of the cool things about calculus is, even though it's really hard, you actually start getting to a level of math where all the math from previous years comes from. So stuff you learned in geometry, stuff you learned in Algebra 1, a lot of that you can derive using calculus, like that's where it originally came from. Alright, so just to sum up the disk method, it's the easiest of the three that we're going to cover, but it has some stuff in common with washer. So horizontal spin, when you want to use dx, is when you have a horizontal spin axis. So how do you remember that? I always like to draw in the little representative rectangle, and whichever way its little width would be, that's my dx or dy. So vertical rectangles have a dx, horizontal rectangles have dy for their thickness. And then of course if you're going to use dx, you've got to have your function in terms of x. Y is just the opposite. Instead of a horizontal spin axis, you got a vertical spin axis. Because if you have a vertical spin axis, you're going around, then that means your representative rectangles, in order to create disks, have to be horizontal, which means their thickness, this little distance, is in the y direction. So it's a dy problem. And of course, if you're using dy, that means your function has to be in terms of y. Alright, so hopefully this wasn't too bad. If you're looking at a problem that uses disk method that's harder than this stuff, just stick around and watch the washer method, because that's what we're going to be doing next in class anyway. You can do all the same problems with washer method, but you can do so much more. So stay tuned.